Hey everyone, and welcome. Today, we're going to dive into a real scientific detective story. It all starts with a totally baffling discovery, this strange orange compound that seemed to break all the rules. And it ends with the chemistry that, believe it or not, powers our modern world. So let's get into it. So, a chemical sandwich. What on earth is that, right? It sounds a little strange, but this question is the central clue in our whole mystery. And the quest to answer it? Well, it didn't just solve a puzzle. It unlocked a revolutionary new way of thinking about how atoms can even stick together. Okay, so our story really gets going back in 1951. A couple of chemists, Keeley and Pawson, were trying to make one thing, and completely by accident, they created something totally unexpected. They made this bizarre, beautiful orange crystal that was also just incredibly stable, and it seemed to defy all the known rules of chemical bonding. It then took another 2 decades for Geoffrey Wilkinson and Ernst Otto Fischer to finally crack the case, which, as you can see, earned them a Nobel Prize in 1973. And this is the star of our show, Ferrocene. This is the wild structure that Wilkinson and Fischer proposed. You've got an iron atom that isn't bonded to just one carbon atom. No, it's perfectly suspended, or sandwiched, right between two flat, 5-sided rings of carbon. I mean, this was totally unheard of at the time, and it sparked a genuine revolution in chemistry. So, at first, people guessed that ferrocene had a simple, direct bond between the iron and a carbon atom. But that just couldn't explain its bizarre stability. It didn't add up. But the sandwich idea? It just clicked. It was a perfect fit. It suggested that the iron atom was being held in place by the electron clouds of both carbon rings, sharing its electrons with all 10 carbon atoms at once. It was an elegant solution that perfectly explained everything. Okay, so proving the sandwich structure was one thing, but it wasn't enough. Scientists really needed to understand why it was so incredibly stable. This meant they needed a new framework, a kind of bonding code, something that could predict which of these strange new molecules would actually hold together and which would just fall apart. And believe it or not, the key to the whole thing was this number, 18. This became the new magic number for stability in the wild world of organometallic chemistry. And that brings us to what's known as the 18 electron rule. You can kind of think of it like the octet rule you probably learned for simple atoms. It's a guideline that predicts when these organometallic compounds are going to be exceptionally stable. The goal for the central metal atom is to get to 18 valence electrons. Those are the outermost electrons doing the bonding, and achieve this super stable closed shell configuration, just like the famously unreactive noble gases. So let's apply this rule to our friend ferrocene and watch how everything just clicks into place. The iron atom in the middle, it contributes 6 valence electrons. Each of the 2 carbon rings brings another 6 to the party. So that's 6 from the iron plus 12 from the 2 rings for a grand total of 18. And boom, the number just works. It's perfect. And it totally explains why this molecule is so darn stable. Now, what's really cool is that solving the ferrocene puzzle suddenly made a bunch of other chemical oddities make sense. And that includes the very first organometallic compound ever discovered, a mysterious substance from way back in 1827 known as Zeise's salt. Take Zeise's salt. This thing baffled chemists for more than 100 years. What you have here is a platinum atom, but it's not bonded to the end of an ethylene molecule like you might expect. Instead, it's holding onto it sideways, bonding directly to the carbon-carbon double bond itself. The question is, how on earth does that bond actually work? Well, the answer is just this beautifully elegant idea called the Dewar-Chatt-Duncanson model. And the key word, the whole idea behind it, is synergy. It's not a one-way street. The bonding is a true partnership, kind of like a molecular handshake. Okay, so let's break down this molecular handshake. First, the ethylene molecule offers up the electrons from its double bond to an empty spot on the platinum metal. Think of it as the first part of a handshake, the initial grip. That's called sigma donation. But here's the magic. What makes the bond so strong is the return squeeze. The metal donates electrons from one of its filled orbitals back into an empty orbital on the ethylene. And that part is called pi-back bonding. And we've got real physical proof that this handshake is happening. And we can see it right here in the bond length. See, in a free ethylene molecule, the carbon-carbon double bond is about 134 picometers long. But when it's in Zeise's salt, it actually stretches to over 137 picometers. So why? It's because that pi back bonding from the metal shoves electrons into what's called an anti-bonding orbital, and that physically weakens and lengthens the bond. It's a totally measurable sign that this molecular handshake is really happening. So, this whole molecular handshake thing, it's not just some cool chemical curiosity. It is literally the engine that powers a huge chunk of modern industry. This special ability for a metal to both accept and donate electrons, to make and break bonds so flexibly, is the absolute secret behind catalysis. Right, so what can it do? Well, it basically allows a single metal complex to act like a tiny molecular machine. It can orchestrate chemical reactions over and over and over again with incredible speed and precision, and usually using way less energy than older methods. Okay, so this super dynamic bonding is what makes catalytic cycles possible. A metal complex can grab reactants from its surroundings in a step called oxidative addition. You can see the metal's oxidation state actually increases. Then it shuffles them around, and finally it releases the finished product in a step called reductive elimination. That returns the metal to its original state, ready to do it all over again. And this cycle, it can happen millions and millions of times, all powered by that flexible molecular handshake. And the impact of this? I mean, it is absolutely immense. From the polyethylene plastics in our water bottles, to the acetic acid used in all sorts of solvents, to the complex aldehydes that are the basis for perfumes and pharmaceuticals. Seriously, our world is built on products made possible by this kind of organometallic catalysis. And to think, it all started with scientists just trying to figure out a weird chemical sandwich. So, think about it. By solving the mystery of this weird orange stuff, ferrocene, and figuring out the bonding in Zeiss's salt, chemists didn't just get an answer to a puzzle. No, they got a whole new toolkit for building and changing molecules. And really, that's the big takeaway here. This kind of deep, fundamental understanding of how the world works at a molecular level, it leads directly to powerful, world-changing technologies. That initial curiosity, just wanting to understand a weird orange crystal, is the same force that now helps us create life-saving drugs and incredible new materials. So it really makes you wonder, doesn't it? Because if the history of science has taught us anything, it's that the next huge leap forward, well, it might just be hiding in the next beautiful, baffling molecule that seems to break all the rules.